Hi everyone. This is the second part of the lesson on integration by U-substitution. This is what we did yesterday. I usually spend 2 days on this, so this is the second day. And today we're basically doing the same thing. The only thing that's new is we have to go back and talk about how do we deal with these endpoints when we're doing this U-substitution process. But let's go ahead and just start with plain old U-substitution here. So when you're looking at this problem, think about what your U should be. Remember, the advice I gave you yesterday was let's always look for the function inside another function. So that's this guy. So I'm going to say that U is equal to x squared plus 2x minus 3. Okay, that looks like a good candidate for U because it's inside of something else. Then we need a derivative of U. So du would be... let's see, 2x plus 2. Technically, that should be in parentheses because you're multiplying the whole thing by dx. And then when I move that to the other side, this becomes 1 over 2x plus 2 du equals dx. Okay, so that's that first phase, right, is plugging in the u values. So now let's talk about rewriting the integral. Okay, if I rewrite this integral, and I'm purposely leaving out the 1 and the 2 for right now. We'll come back and talk about those in a second. But this thing that's underlined, I get to replace that with u. So this is a u squared times an x plus 1 times, in place of dx, I'm going to put 1 over 2x plus 2 du. Now, the purpose of U-substitution is to get those x's to disappear. And this is a little bit tricky for figuring out how those x's disappear because they're not quite ready to cancel out because of the addition that's in here, right? I can't just cancel this x with this x because this is really an x plus 1. So you have to think outside the box a little bit here. This 2x plus 2 could be rewritten as 2 times x plus 1. So I factored out a 2 there, and that now allows me to get rid of my x plus 1s. Okay, so sometimes you've got to do a little bit of algebra there. Now I'm going to rewrite this integral all cleaned up, but before I do that, I do want to talk about these endpoints. So these endpoints back here, the 1 and the 2, those are referring to x values, right? Like these are, places on the x-axis where we're going to start and stop integrating, okay? So along the x-axis. The problem is that when I get over here, I'm not doing an integral of x anymore. I'm doing an integral of u. So we need to change these from x values to u values in order for them to work inside my integral. So we have to think about what information do we have that lets us turn x into u. Well, that's actually the very first thing we wrote down right here. This right here is giving me the conversion, right? This is how I switch x's into u's. So that's what I'm going to do is I'm going to plug my endpoints into this expression for x. Now, most of the time you're going to be able to just do this in your head, but for the sake of your notes, you might want to write down like what I'm doing here. So for the 2, I'm going 2 squared plus 2 times 2 minus 3. So that's 4 plus 4 is 8 minus 3 is 5. And then for 1, I'm going 1 squared plus 2 times 1 minus 3. So that's 1 plus 2 is 3 minus 3 is 0. Okay, so when I switch out my x's for u's, I also have to convert my endpoints. So now what my integral says is give me an integral. I've got this 1/2 sitting here. So I should have snuck that in before I wrote this down. I have a 1/2. My endpoints are 0 and 5. And then inside the integral, I've basically gotten rid of everything else except for this u squared. And this is a much more doable problem than this original thing, right? I've rewritten it this way. Okay, so let's take our antiderivative. Don't forget, that's the whole goal, right, is to get that antiderivative. So I'm going to say 1/2. And then antiderivative of u squared is 1/3 u to the third. Now, here's the good news. This is one little off-ramp that we get to take. When I'm plugging numbers in, all right, endpoints, well, I pointed to the 1 and the 2, but it's really going to be the 0 and the 5. I already converted these to be values of u, not values of x. So I don't have to go back and plug this u thing back in. Okay, I can just keep my antiderivative right here. I don't have to do that last step we usually do, because instead of doing that last step, I'm just going to plug numbers in. Okay, so into this antiderivative, I'm going to make this a 1/6. Hope that doesn't bother you. 1/2 times 1/3, u to the third, from 0 to 5. And that's going to be 1/6 times 5 to the third minus 0 to the third. So I'm just plugging in the 5 for u. I'm plugging in the 0 for u. Well, 5 to the third is 125, and then times 1/6 would just give me 125 over 6 as a final answer here. So the only new thing today is convert your endpoints to u values and then stop before you plug your u back in. That's where you can just plug numbers in now instead. Okay, let's try the next one. And full confession on the next one. When I did this one in class, I stumbled a little bit over what u should be. This is a tough one to figure out what u is. So my first instinct was to make u be cosine, because this is like a cosine inside a, well, it's like a 1 over cosine inside a square function. So I said, well, let's try cosine. I didn't think cosine would work. I did actually have a student do it with cosine, and they were able to figure it out. There is a way to make it work with cosine if that was your u value. But I threw in the towel and decided I was going to try something else. So I think then I tried secant. Secant didn't really get me anywhere. And then the last thing I tried was tangent. So I just want you to realize that, like, sometimes it's hard to know what u should be, and you have to just try something and see if it works. Okay? And if you're starting to understand how U-substitution works, maybe you can think ahead about why tangent is going to be a helpful choice here. Okay? So I'm going to say that u is tangent of x, which means du is the derivative of tangent, which is secant squared of x. All right, that should be looking a little bit convenient. When I move secant squared to the other side, I can write it as 1 over secant squared of x times du equals dx. And now it's time to rewrite my integral. So my tangent of x is now u, and then I have a secant squared. And then I'm going to multiply by 1 over secant squared. Well, that's convenient. Times du. I can see right now my secant squareds are going to go away. Last thing I need to do, though, here is convert my endpoints. And so that means I'm taking the 0 and I'm taking the pi over 4 and I'm plugging them into this u expression. So I'm finding the tangent of them. If you have to sketch yourself a unit circle, go ahead. But tangent of 0, we should know that tangent of 0 is just 0. And then tangent of pi over 4, if you think about like your 45 degrees there, tangent of pi over 4 is just 1. So that let us convert those to u values instead of x values. Now, let me just jot down here how I got this. This I did tangent of pi over 4. And this I did tangent of 0. Okay. So now my integral really just says, I need an integral from 0 to 1 of just plain old u. I know that's tempting. That looks like it's really easy right now. Don't forget, this is telling us we still need an antiderivative. So an antiderivative of u would be add 1 to the exponent. So that's going to be a u squared and then divide. So I have 1/2 u squared taken from 0 to 1 That leaves me with 1/2 1 squared minus 0 squared. Well, that's just 1, right? So 1/2 times 1 is just 1/2 as a final answer. Okay, last one. Strongly encourage you to pause right now and try this one on your own. Let's think about what U should be here. Another strategy, if you can't see that like function inside a function thing, sometimes if it's a fraction, it's helpful to make the denominator be your U value. Because by putting that denominator as U, you're kind of saying like, hey, that's inside like a 1 over x function, okay? And hopefully that derivative will cancel that x that's on the top. And maybe you can even look ahead and see that that's going to happen. So if U is x squared plus 4, then du is 2x. Swap that over to the other side, and you end up with 1 over 2x. du is dx. Rewrite our integral. So now what I have left here, the x on top is still there. X squared plus 4, that became my u, so that's just a u. In place of dx, I'm putting this thing, 1 over 2x du. And that step right there is going to allow me to get rid of this x and this x. I do still have a 1/2 floating, right? So I'm going to have a 1/2 integral. This integral would be of 1 over u du. That looks easy enough, right? Let's go back and flip our endpoints real quick. So I'm plugging 5 into x squared plus 4. That's going to be 29. And then I'm plugging 2 into x squared plus 4. So that's going to be 4 plus 4 is 8. Okay, so those are my new endpoints. Now I need an antiderivative. My 1/2 gets to come along for the ride. So 1/2, and this would be an antiderivative that's natural log of u taken from 8 to 29. So I'm plugging this in, plugging this in. Don't freak out about the idea of doing natural log of 29. I don't expect a decimal here. Natural log of 29 is a perfectly valid answer. I would probably just write that 1/2 out in front of everything. So I would say 1/2 times, and then this would be natural log 29 minus natural log 8. And that's a perfectly fine answer. I'm happy with that. That's all numerical. I did have some people in class that wanted to combine these two natural logs and make it like a natural log of 21. There is a way to combine natural logs, but it's not by just subtracting. Remember that logs are really exponents in disguise. And so you subtract exponents when your powers are being divided, right? So if I wanted to combine these two, the way it would look is it would be 1/2 natural log of not 29 minus 8, but 29 divided by 8. Okay. I don't care if you take that step or if you just leave it like this, but just know that in a multiple choice setting, it might show up this way. So you'll want to be able to recognize that. Okay, that's it for today. We're just going to try a few more of these tonight with the endpoints so that you can kind of, clarify in your mind what to do with those. And then we still have a couple more methods of integration that we need to talk about over the next couple of days. But this should do it for U-Substitution. So after you're done with this lesson, after you're done with this homework, I'm really expecting you to be pretty confident about these. If you're not, then we need to talk. Okay, and I can help you out with it. So please make sure you see me in class if that applies to you. Otherwise, good luck and have a great night.